Hey everyone, my name is Brian Sickles and I am the product manager for Kubernetes and containers at Vertica.
And I'm Matt Spilchen. I'm a senior system software engineer at Vertica. I'm the lead for the Kubernetes project.
Great. So today we'll be discussing operationalizing Vertica with Kubernetes containers with you all. All right, great. Let's get started. As many of you might be aware, back in August of last year, we officially released open source support for Kubernetes as a way to deploy Vertica. We wanted to support the future strategies of our customers, including being cloud native, utilizing microservice architectures, or needing an easy way to integrate with their existing Kubernetes deployments. I also wanted to say that Vertica on Kubernetes is already being used in production with some of our customers. We deploy Vertica on Kubernetes using stateful sets that allow us to persist and load balance data across nodes. This all wouldn't have been possible if we hadn't revolutionized Vertica deployments through our release of separation of compute from storage. This means that Vertica on Kubernetes only runs on deployments of Vertica where there is a separation of compute and storage on-prem or in the cloud. After we released support for Kubernetes, we decided to develop an operator to help deploy, monitor, and manage Vertica in an automated fashion. Easily installed via Helm or operatorhub.io, our operator currently supports S3 type storage, HDFS, Azure Blob Storage, and Google Cloud Storage. We also support some of our more popular Kubernetes managed services, including Amazon EKS, Google GKE, Azure AKS, and OpenShift. In order to help you manage your Kubernetes clusters, the operator utilizes automation to keep your Vertica database in a predefined healthy state within a Kubernetes cluster. Current operator functionality includes near zero downtime upgrading to a new version of Vertica, 11.1.0 and on, restarting failed nodes, auto-scaling up or down nodes or subclusters, as well as reviving a database. We are constantly working on improving the maturity of our operator, and besides backup and restore functionality, our operator is close to being fully mature according to the Operator SDK framework. As we continue to build out our support for Kubernetes, we have seen customer and community interest. Since September 2021, we have seen over 1,500 downloads of our Kubernetes operator and over 1,200 unique repository visits. It is extremely easy to get started with Vertica and Kubernetes. You can currently deploy in any on-prem environment, as well as in the cloud with a managed service. First, you need to deploy the Vertica Kubernetes operator that you'll deploy your Vertica cluster in. This operator includes the logic to automatically keep the desired state of your cluster as defined in your custom resource. This would include creating the Vertica database, restarting nodes that crash, or restarting the cluster if you lose quorum. Scaling by changing the sizes of your current subclusters, or adding or deleting new subclusters, as well as reviving or upgrading your Vertica database. You can customize the desired state of your Kubernetes cluster by modifying the custom resource. As soon as you apply your defined custom resource, the operator will create your Vertica database. In this example, a 3-node database is created within the Kubernetes cluster, where each Vertica pod shown here contains a container that runs Vertica. In order to manage the desired state of the Vertica database, the operator monitors the cluster, and when state changes, the operator will correct it. Finally, within each subcluster, you can define a service type that will allow a client access to, for example, connect and run a query against Vertica. The operator manages a single namespace, so if you want multiple namespace databases, you need multiple operators. Here, the subcluster is one stateful set, and each service object would map to a subcluster. Finally, we only offer the ability to create a Vertica database in a Kubernetes cluster where the compute is separated from the storage. As you can see, Each node has local persistent storage. This would contain TPO, local catalog, log files, and config files, which are things that need to survive between pod rescheduling. This persistent storage acts as a depot for each node to process and distribute the hot data from the communal storage that exists outside the cluster. This also makes sure that if a node were to crash, then all the local data would persist in the local persistent volume and can be reattached to the node once that node is back up and available. Now over to Matt.
Thanks, Ryan. So to start using Vertica and Kubernetes, you first need to deploy the operator and the custom resource definition. The operator runs in its own pod, and an end user manages the deployment by creating or modifying a custom resource. The operator will do whatever is necessary to match the desired state in the custom resource with the actual state. So you have two choices here for deploying the operator. You can either use Helm or OLM. They both have their strengths and weaknesses. Helm provides the most flexibility, as you can tune various parameters to get the exact deployment you want. For instance, if you're running an air-gapped cluster that doesn't have access to the outside network, you can use a Helm parameter to get to the operator container from an internal registry. I consider OLM as sort of the Red Hat way of managing an operator. It gives you the ability to automatically upgrade the operator once we publish a new version. This would be similar to your phone, where apps in the App Store automatically get updated as software vendors publish new versions. This is what you'd use if you're running on OpenShift too. There isn't as much control about the deployment when compared to Helm, but should be fine if you're okay with using the defaults. When we deploy the operator, we install the custom resource definitions so that you can start creating your own custom resources. We currently offer two. VerticaDB manages the state of the cluster, and VerticaAutoscaler manages how the horizontal pod autoscaler will integrate with Vertica. I'll go over the details of both of them in a bit. When you deploy the operator, you also run and register a Kubernetes webhook. Kubernetes will call this webhook whenever the custom resource is created or modified. This kind of ensures that the states in the custom resource change in a valid way. The operator only looks for custom resources that were created in the same namespace the operator was deployed in. You can run the operator more than once, but it has to be in separate namespaces. Within a namespace, you can have multiple custom resources, but the operator runs single-threaded. So to get the best response time for admin events, you typically would want one operator for each database. Generally, you need elevated privileges in the Kubernetes cluster to deploy the operator. For instance, creating the custom resource definition and necessary privileges for the operator through service accounts and roles. We publish YAML manifests for these things outside of Helm. So Kubernetes admins can use these to set up a cluster so that the operator can be deployed by users that only have access to a single namespace. I'm going to dive into the VerticaDB custom resource a bit. So this is the custom resource that you would use to create a Vertica cluster that is managed in Kubernetes. Each custom resource that you create is for one database. If you have multiple databases, you will need to create a custom resource for each. We can only use Vertica when it separates compute from storage. So this fits better in cloud environments because unlike enterprise mode, you don't need to worry about moving data around as you scale the cluster. You have two options when you bootstrap the custom resource. You can create a brand new database, or you can bootstrap from the existing database through the revived-db command. We even offer a tool that you can run that will connect to an existing database. It could be on-prem or in the cloud, and it will generate a custom resource to allow you to revive the database in Kubernetes. The communal storage needs to be accessible from Kubernetes, but it doesn't need to exist inside Kubernetes. We support all the communal storage formats that the Vertica server supports. So it can be object storage that has S3 compatible API, any of the major cloud vendors like AWS, Azure, or Google, or it can even be HDFS. Rather than take you through each field we have in the custom resource, I'm going to do a simple demo to show how easy it is to get up and running in Kubernetes. Okay, so I'm going to show you just basically a brief introduction to our VerticaDB custom resource. just going to show an example of reviving an existing database and seeing how it's run in Kubernetes. So I already have the database created, but I don't have it deployed yet in Kubernetes. I do have the operator running in my namespace, and I'm going to basically run this YAML manifest. So this is our custom resource VerticaDB. And let me just kick this off, and then I'll get into some more details about the contents of this. Okay, so I created this custom resource. You can see the windows on the right are sort of status updates. You can see what's happening. And this is it's a very basic custom resource. There's a lot of options here that I omitted, but the important ones, or some of the required ones, are here. So as mentioned before, you need to bootstrap this database. I'm going to be using Revive, so the database must exist in this path. I've set this up on basically like a MinIO communal storage, and I've also sort of linked it with some authority, like secret and access key, to be able to access this MinIO. The init policy here defines how to bootstrap it. So I'm doing a Revive. You can also do create as another option. And within the custom resource, you define the subclusters that you want to see. So in this case, we have two subclusters, each size 3. One's a primary and one's a secondary. They both use node port with a unique node port number. I'll get into this a bit more later to see how that plays out. So you can see on the right here, the events that the operator has done the Revive successfully. Now it's in the middle of starting, and you can see it just completed the start of the database. And these are all the pods that are running. So you basically have one pod per Vertica node. And then we have a few service objects, and then a couple stateful sets. The stateful sets apply basically one per subcluster. So you can see within the name is the name of the subcluster. So we have SC1 over here, and you can see this is subcluster SC1. And then the 3 pods that are in it are the first 3. Now everything's up and running. I've created the service objects. Again, you're going to have one per subcluster, and I've created them to be node port. And this is just for demo purposes, so that I can access the Vertica within it from my laptop. So I'm running the laptop. I'll be able to connect in through a well-defined port to be able to connect to it. So let me do that right now. I am running Kubernetes within Docker, so the port numbers aren't going to line up to what's in the custom resource. So I'm going to use port 5433. That's going to direct me to port 3001 within this Kubernetes cluster and get access to this one subcluster. So now if I were to see what node that I actually connected to, node 2, so you can see node 2 will be this one right here. So when you connect in to these service objects, it does like a round robin among the ready pods. So if I had have exited it out and got back in again, I might have gotten a different node. So it's kind of arbitrary which one is picked. The only stipulation is that the pod has to be ready, meaning Vertica is running. And because I revived, there's already existing database, so I have a ready-made queries to see that it can access that. It's basically a small data set of countries that are in Europe. I'm just going to order the top 10 by population. Whenever you, so I'm in subcluster 1. If I were to exit out and try a different port that maps me to the second subcluster, right, and I enter that in, and then reissue you could see what node you're selected to. Now I'm on node 4, and that's one of the nodes in the secondary. The operator also handles restart capabilities. So if if Vertica went down one of the Vertica nodes went down, it'll actually restart it. Let's do a quick demo here. I probably won't wait for everything to come back up, but just to give a sense of what the operator will be doing. So I'm going to go ahead and delete SC2.1, this one right here. Delete the pod. You can see that the pod is scheduled to come back pretty much right away. Just takes about 10 seconds or so, and then it'll start running. Yes, now it's running. The one thing to point out here is that because the pod's deleted, the Vertica process that was in it is gone. And when you restart the pod, the Vertica process doesn't come up right away. We have to run admin tools command. That's what the operator does. It's going to run admin tools command to get Vertica running on that. The ready probes are there for service objects so that a service object won't route traffic to this this one pod that's down. Like if I were to go back into the secondary subcluster and select what node I connected to, it's not going to be one that's down. Node 4, so it's that first one there. So you still have access if I were to issue my query. Let's see if I still have access to the data. You can see I still have access to the database is still up. It's just in the business of restarting this one pod. So there's actually a delay between when the operator actually will issue the correct admin tools command and it's basically waiting for timeouts within spread so that the Vertica cluster is aware that the pod is gone. And now you can see that it's actually in the middle now of doing a restart. And once this finishes, the ready probe will go to 1, and then service objects can route traffic to that pod again. And that just gives you a flavor for some of the a basic intro stuff to the custom resource. So now we'll talk a bit more about some of the more advanced features. The first advanced feature I want to show you is around upgrade. So the VerticaDB custom resource has a parameter that lets you specify the image to use. So whenever this image changes, it forces the operator to go through upgrade logic. So prior to 11.1.0, this upgrade was always offline. This meant that the entire cluster would be stopped. We would reschedule the pods using the new image, followed by a cluster restart. Starting in 11.1.0, we added the ability to do the upgrade online. So it's an online in the sense that nodes that haven't been upgraded yet will be in read-only state, allowing SQL queries to be issued. So if you have a workload that does writes, such as an ETL, they must be taken offline for the upgrade to succeed. The way it works is that it will first stop all the nodes from the primary subclusters. This forces the nodes in any secondary subcluster into read-only state. It will then restart the primary nodes with the new image. We then proceed to stop, reschedule, and restart the secondaries. We do this subcluster at a time. Access to this cluster through the various service objects will seamlessly redirect to a subcluster that is up. For instance, if you had a service object for a primary subcluster, that service object routes traffic to one of the secondaries while the primary is being restarted. If you have some control over what subclusters are used for the routing. If you don't have a secondary subcluster, you even have the option of creating a temporary secondary just for the upgrade. The online upgrade will take a little extra time, so the custom resource has an option to allow you to pick between the two methods. By default, it will automatically select online if the Vertica version you are starting with is 11.1.0. I'm going to go into more details to describe how the online upgrade works by showing a little demo. So I'm going to demo online upgrade. I have a running system already, so let me just explain what I have here. So there's 2 subclusters, Pry1 and Sec1. Each have 3 pods in them. I have upgrade status of blank because there's nothing to report yet. I show the image list that each pod's running. They're all running with the tag of V1. Then I show the node list, which is just our catalog state for each node. It shows whether it's up or down, if it's a primary subcluster, and if it's in read-only state. And then at the bottom, I have active connection. So I continually connect to each subcluster and just show which node we're connecting to. And this will become more important when we actually drive the upgrade. So to drive the upgrade, you simply just have to change the image name in the custom resource. So I have a patch command that I run, and it's going to change the image to use a tag of v2. So once I apply this, the upgrade is going to commence, and things happen quite quickly off the bat. You'll see that we already have scheduled pods for the primary subcluster. They're all in pending state, so the pods are about to start soon. But you can see the image list already has v2 associated with it. So now there are all the pods for Pri1 are running. Obviously, Vertica is not running in them. And then right off the bat, we kind of wait for the read-only state to show up in the secondary. So there's a pause here. It's just waiting for spread timeout for it to realize that the primary is down, and then secondary will transition to read-only state. There, so the primary nodes are down. The secondary nodes stayed up. And you'll notice that the read-only state for the secondary is set to true. So now we're in the process of restarting the primary subcluster through admin tools. So notice none of the Vertica is running on those pods. The active connections, though, we're still trying to connect. We are connecting into vPrimary, but we're actually getting routed to the secondary subcluster. So this is expected. We're getting routed to a subcluster that is up. Now, if I were to run a VSQL command and just show which node I connect to, you'll see we connect to node 5, which if you look in the catalog, node 5 is one of the ones in the secondary. Now I'm going to leave this connection up just to show the draining aspect, because once the primaries are restarted, then it'll go in and restart the secondary. And I'm just going to show that the connection we have is actually going to block that part. So you can see the primaries are up, node states are back up, but now we're draining for the secondary subcluster. And it's because we have this connection open that it's not proceeding. So if I quit this, disconnect, you'll see then that the upgrade will continue. Now it's restarted the secondary, so it's deleted all the pods. They're in pending state. The image for secondary are in v2 now, and the catalog state shows that they're down. If you connect into the secondary, you'll notice that it gets redirected to the primary subcluster. Gets load balanced among the primary subcluster, and this happens as long as the upgrade is restarting that subcluster. Now, if you have multiple secondary subclusters, it'll do this restart sequentially. If I go back and reconnect, I can show you which node I connect to by doing my query here. So we know we connected to node 1, which is the first node in the primary subcluster. So we're in this state until the secondaries do come up. That should be fairly soon when it does come back up. And when they do come up, we'll update the service object so that the secondary redirects its traffic to the secondary subcluster, as you would expect. So there, the secondary nodes are up. Everything's fully online. The ready states will switch there. They switched. Upgrade status is cleared. So basically the upgrade is done at this point. And then the connections to the secondary are what you would expect. And that's the end of the upgrade. Another advanced feature I wanted to get into was the integration with the autoscaler. Within the Kubernetes ecosystem, they have what is called a horizontal pod autoscaler. It does what its name describes. Based on some metrics that you choose, it can decide to scale up or down a Kubernetes object by changing the number of pods within it. We just added support for this to work with the VerticaDB custom resource. It's available in the latest release of the operator. Within Vertica, you have two main use cases for scaling. You can choose to scale out by creating new subclusters. Your existing clients can then load balance between the new subcluster and the existing ones. This type of scaling is ideal if you have a lot of smaller dashboard queries that are overloading the system, causing decreased throughput. Scaling out by creating a new subcluster will allow more queries to be run. Another way to scale is by growing the size of an existing subcluster. This type of scaling is ideal if you have long-running queries that would benefit from having its query distributed over many nodes. We recommend that the shard to node ratio be 2-to-1 or 3-to-1. If the actual ratio is below this, the queries could benefit by having more nodes to run on. To support these two different use cases, we added another custom resource called the VerticaAutoscaler. I'll go into this new custom resource in some detail on the next slide. I just wanted to finish off this slide by mentioning that we integrate with the horizontal pod autoscaler, but we aren't really opinionated about what metric you use to trigger autoscaling. How fast to scale up or scale down. These are all workload dependent, so you'll need to figure out for your specific use case. It is best to think of the VerticaAutoscaler as an object that connects a VerticaDB with some scaling behavior for a subcluster. So because the VerticaDB has many subclusters, you can have many VerticaAutoscalers all connected to the same VerticaDB. Here's a sample VerticaAutoscaler. A few things to call out. So the VerticaDB name, that field connects this object to a VerticaDB that you want to scale. Granularity determines what type of scaling you perform. We currently support scaling by subclusters or by pod. The service name acts like a selector for a subset of subclusters that this applies to. So it refers to the name of the service object that does load balancing between the subclusters. A key thing to note here is that the client connections do not need to be adjusted for scaling operations. Clients will continue to connect through a well-known service object. If the autoscaler adds a new subcluster, the clients continue to use the same endpoint. It will just load balance with the new subcluster. I want to take you through a demo to really show you how this is integrated. Okay, so I'm going to take you through a demo for the autoscaler integration with Vertica and Kubernetes. So first I'm just going to sort of describe my system here, and then I'm going to get into the actual workload of doing an autoscale. So I'm running in GKE. I have 7 nodes. And I already have Vertica installed, and it's running. I'll show you what I have here. So it's I have a single subcluster with 3 nodes in it. So the database is already set up. And in terms of the workload that I'm going to run to drive the scaling, I use Locus. Basically, it's just a load stress tool. And we're just going to run a bunch of clients at Vertica to get a workload running. Let me kick that off now. So I'm going to run with 125 clients. So I'm running, essentially it's like a TPCDS workload. So query 41 is the one I chose for this demo. And the charts are sort of more interesting here. We're basically in the process of scaling up to 125 clients. You can see the top chart here is the total requests per second. So this is the main one we're going to look at. So we're at about 60 requests per second for 30 clients. And then down below is sort of the response time that you'll see. Initially the depot is going to be warmed a bit. So the response time per query will kind of go up, and then you'll see it come down again once everything's warm. But one thing to point out here is we've kind of plateaued in terms of requests per second. So we're at about 55 users, and it really hasn't changed. So we're still in the 50 to 60 band. So that's kind of an indication that the workload we're running is it's too big for the system that we're running on. So let's go back to the system for a second. So within Kubernetes, you can get metrics in terms of the CPU and memory usage per node. So I'll just show that. So you can see we have 3 nodes are sort of active. And the way I've set it up is that Vertica Pod will only run on you only, for any given Kubernetes node, you only have most one Vertica node on. So we have the three Vertica nodes spread across three Kubernetes nodes. So you can see here that the CPU is sort of getting hit. The memory doesn't seem to be a constraint in this workload. So we're just going to focus on the CPU percentage for this case. So as I mentioned, in order to drive out auto scaling with Vertica, you have to describe what sort of scaling you want. And so that's where this other autoscaler, VerticaAutoscaler custom resource comes in. So I'll kind of show what I'm going to run with. So this is the new CR that we're going to run with. It's pretty simple. Basically, this VerticaDB name, that's the glue back to the VerticaDB. So vert here is the same vert there. We're going to scale by growing subclusters. So we'll see this, our scaling will go from three pods on one subcluster to 6 over 2. And this in the service name here, pry1, that's sort of the connection between the different subclusters. So you'll only ever see one service object, and it'll service multiple subclusters. So if I do a get service, use vert pry1, this is the service object that clients are going to connect to. Currently, they only route to the one subcluster, but once I do the auto scaling, they'll actually route to either of the subclusters that we're going to scale it to. So let me go ahead and apply this custom CR. And then let me get Vertica to show the objects. So this is the vert is our database, sort of as we saw it up here. This new thing, this AS is our autoscaler object, and we're going to scale by subcluster. Current size is 3. The target is 3. We'll have Kubernetes changes automatically based on metrics that it gathers. So that's sort of the next step. The next step, now that we've created this object, we're still not quite set to autoscale. We have to use the kubectl autoscale command, and we're going to run it on this AS object. This ends up creating another object called the horizontal pod autoscaler, HPA. So let me just run the command to start the autoscale. So just to describe here, so we're going to autoscale this VAS AS is this object here. We're going to set a constraint here that it can't be less than 3 pods and it can't be more than 6. And the metric we're going to use is the CPU percent. So we're going to try to target CPU percent of 50. And then if we go over that, that's when scaling is going to happen. So let me go ahead and run that. Now there's going to be a new object created, this HPA. So let me So this is the HPA. At some point, it's going to wake up and you see it. It saw the target of 50, and currently it's at 93. So it's figured that it needs to scale out. So it's already made that distinction that we need to grow another subcluster. So that should have already happened. So if we go in and we edit the vert, go to our subclusters, we should see. So this subcluster here is the first one we added, and then here's another one that was added here, and it has a different name, AS1, but everything else is the same. The key thing here is the service name pry1, so that glues them together. So if you'll see that now we have 2 subclusters, and we're in the middle of doing an add node for those. So let's check if the pods are running. Yeah, so you can see now we have 3 extra pods for the new subcluster. They're currently not up yet. They're in the middle. So let's see the events that are happening in the VerticaDB. So we're in the middle of calling add node right now. So we've been at it for a bit, 45 seconds. So that should finish soon, and then we should be good to go. So there we go. So we've finished the add node. So now the cluster is basically scaled out to 6 nodes. So let's go back to workload and see what's happening here. You can see there's a bit of a dip here. Let me explain that. So to run a query, the compiled plan must be sent through our consensus layer known as spread. Because we're adding new nodes to this cluster, this compilation must wait for spread to be updated. So that's why we see query throughput drop. It's only temporary, and you'll see the query runtime quickly come back up. As you see it here. So with the new subcluster online, you can see now that the total requests per second has jumped. So we're at about 134, and before we were in sort of like the 60 to 70 range. So we kind of almost doubled it. And it's that's what you expect because we have doubled the number of Vertica nodes as well. Now I should mention, let's go back and have a look at the CPU usage on the Kubernetes nodes. Now you can see it's spread across 6 nodes. And actually the CPU percentage is still quite high. So based on this workload, if I didn't cap the max pods to be 6, I probably would have decided to scale again. But I think I'll stop there. I think this is a good demonstration of the autoscaler, just to get a sense of how it's integrated. So that wraps it up for some of the features I wanted to take you through. Over to Ryan to cover our roadmap.
Thanks, Matt. So here at Vertica, we are always continuing to grow our Kubernetes capabilities and operator maturity. I want to touch upon some Kubernetes and operator functionality we plan to work on in the future. This is a disclaimer that Vertica, our product roadmap, is not final and planned functionality is subject to change. As mentioned previously, we are planning to work on improving the backup and restore functionality, as well as the functionality to restore from a backup using the operator. We are also looking into support for VMware Tanzu and Rancher. We also are looking into integrating Prometheus monitoring, not just with the operator's autoscaling functionality, but also with the core Vertica server. Finally, we actively review our Kubernetes repositories for community involvement to help improve and make our Kubernetes support more mature. Since we are open source, please feel free to contribute code or request a feature on our GitHub repository for Kubernetes. I've added a link to this Kubernetes repository above for your reference. Thank you.